And we'll move on to our final presentation of this year's Fall Symposium. And today we have Brian Barjenbruch, who's the SU in Omaha, joining us to give us some freezing rain updates and insights. And you've heard Brian and Chris Sanders' name mentioned several times today in this presentation. They did some real seminal work on freezing rain accumulation. And so I want to thank Brian for joining and sharing with us today. Brian's playing hurt, so thanks for sticking in there, Brian, and take it away. It's all yours.
Naturally. Unmute. There we go. All right. Well, thanks for having me. I've got a presentation here that hilariously will not work in full slideshow mode, but thankfully it works in this slightly updated version. Chrome died like 4 times on me here in the past 5 minutes. So we're going to hope for the best. And we're going to talk freezing rain updates and insights. And I'm going to admit that this is heavier on the insights side of things. So just going to kind of blast through the world of freezing rain, and I hope that you all find it beneficial, and if not, I'll answer a lot of questions at the end. So onward. So I want to start off with a lot of common questions and misconceptions about ice. There are a lot. I think we probably make ice more complicated than it needs to be. So I'm hoping to kind of quell some of these a little bit, kind of settle down, make you a little more comfortable with the world of freezing rain. Part of the problem is it's rare, relatively rare compared to a lot of other things we forecast. So a lot of the questions I hear over the course of a winter, I'm sure Chris does too, I'm sure lots of other people too who are involved with winter weather. Why are we forecasting flat ice? Or the opposite, why are we forecasting radial ice? How am I supposed to report this ice amount? Why is this so confusing? That's actually a legit question. Will this forecast lead to power outages? That's a really important question. And in the same breath, you can ask, is this an ice storm? Why or why not? One of my favorites, why is ASOS reporting ice and a temperature of 33 degrees? Great question, right? It shouldn't do that, but it can and it does. Why is freezing drizzle on a windy day reporting so much ice? And just plain, are we doing this right? I don't know all the answers, especially to that last one. But the fact is we are doing it. And so we're going to do it as good as we can. So let's get into the other hand, which is a lot of misconceptions about ice. These are false statements, okay? Misconceptions. The ASOS icing sensor can't be trusted. That's false. It's peer-reviewed. There is some quality information and observations backing up what the ASOS sensor measures. It might be annoying at times in how it reports that ice and some specific scenarios that are outlined within the peer-reviewed research where there can be errors introduced. But for the most part, it's pretty accurate. Otherwise, we wouldn't have released it as the Weather Service. Another popular misconception is that ice can't form at a temperature greater than 32. It can. If you get down to the micro scale, you're looking at differences in wet bulbing on the edges of droplets. And so you can get ice to form at 33, 34 degrees Fahrenheit. This one's probably my favorite currently. A quarter inch of ice will cause ice storm conditions. No, it might if there's a lot of wind. It will not if there's not wind. And that depends on your definition of ice storm. As our definition stands, it's for a quarter inch of ice in most of our CWAs. But how are we measuring that ice? Things like that, right? The questions are out there. Some people I've heard think any ice at all should be called an ice storm. My least favorite event I've ever forecast or not forecast was an extremely light freezing rain event where there were catastrophic impacts for some folks out there. So it's a thought or misconception. One other misconception is that 1/10 of an inch of ice always causes more impacts than 1/100th of ice. It might be the opposite in some cases. Thought that freezing drizzle can't cause power outages. I personally have lost power on a freezing drizzle event. This one's just silly, but FRAM is perfect is definitely a misconception. But also, anyone who says FRAM is terrible, that's also a misconception. It does a job it's designed to do. And so I'm going to talk about a lot of these more. When it comes down to it, These are all misconceptions, so disregard them, especially if you've got them living in your brain. My thoughts and the folks I talked to, and we've got the freezing rain team that just spun up this fall, or late summer, I guess we'd call it. We're trying to address a lot of these things. And even just right now, I think we as National Weather Service meteorologists and employees, we can improve ice reporting and prediction and messaging by doing some simple things. For starters, let's simplify the terminology, and let's be very clear in our messaging exactly what we're predicting and why it's important or why it might be important. Focus on the impacts. It's what we're doing in everything. I think we can be more confident in our assessment of those impacts with ice. We've got some education we need to do. So maximizing understanding both here for this crowd that I'm speaking with, and also outside our doors for our partners, maximizing their understanding. We really need to improve research efforts. There's a lot of room for some really good research to be done on the impact side of icing and the impact outcomes, and there's not a lot of time to do it. So for anyone who's interested in that, please reach out to me or Chris or whoever. I'm happy to steer you in the right direction to kind of hopefully make some progress in research efforts with freezing rain. I'd be really sad if the FRAM doesn't get overwritten in the next couple of years by new research. And that's the honest truth. I think it can be made better, but we have to keep incrementally improving on these prediction methods. And then improving the ice storm warning criteria. I'm pretty sure this is a big one, and that's not one we can do right away. I think it's the improving of research efforts that has to lead to that. So there's work to be done, and I'm here to encourage anyone listening to help with that work if you're interested. All right, but let's digress back a little bit. And I promised that I would talk about ice and things you need to know. So for this coming winter, let's focus on ice-related things you need to know. And if I don't hit anything that you think you need to know on this list, please reach out and I'll try and have a semi-entertaining discussion with you about whatever that topic might be. I'd really enjoy it. Okay, first off, flat versus radial. I promise that this is not as complicated as it seems. We make it more complicated than it needs to be a lot of times. And if you're mad about it, blame geometry. It's, sophomore high school math, at least for me, I guess. I don't know, probably some of y'all did it in like 6th grade. Blame geometry for flat versus radial. Be very clear in your messaging and observations. Just be clear. Be clear. We have the data. We have the information. Provide it all and provide it clearly so that the external partner or the internal person knows exactly what we're talking about. All right, so here's that geometry I promised. I want you all to picture being a raindrop. Okay, you're falling through the air. It's a lovely day to fall. You were cold aloft, you got warm, you melted, and now you're still melted and you're falling through much colder air. And you're thinking to yourself, I would like to land and freeze. Okay, so now look down and you see a wire. Oh, there's electricity running through that wire. It's a power line. Perfect. Okay, you have a very small amount of surface area that you're looking down upon where you as a raindrop can contact that power wire. Oof. So again, you have a very small surface area that you can actually impact that when you're looking down. As you impact it, let's say you make direct contact. You were super excited about landing on that power line, and so you did. Okay, you made contact. At that point, you are going to spread around the entire surface area of that power line, of the cylinder. That's why if you landed on, say, I don't know, a patio table, you would freeze into a greater thickness than if you landed on a cylindrical object, such as a power line or a branch, and you spread around it. In pure geometry, the exposure area, or that cross-section that you might hit as you're falling, is 32% of the cylindrical surface area that you're going to spread around on that item. Now, here's where it gets weird, right? And this is annoying. I didn't design it or do it, so I don't want to take credit for that annoyance. The ASOS icing sensor did a huge statistical side-by-side study of tons of observations. The sensor on average measures 39% the radial thickness will be 39% of what the sensor measures as a flat ice accumulation. So it's pretty close to pure geometry. But I just want to reiterate one more time. I don't want to make this any more complicated than it needs to be. The thing we need to know, because that's what we're talking about here, is that the surface area of a cylindrical object is quite a bit more than if you just land on the flat object of the same cross-sectional space. So bottom line, your radial ice thicknesses, as predicted by the FRAM, because it's statistical, are going to be about 40% of what the thickness would be if you were to measure it on ASOS or on a flat surface. I've gone out and manually measured these things, and it's pretty darn comparable. So again, I feel kind of bad for giving you these last two bullets here, but the biggest thing I want to put onto people is that it's not that complicated. It's just a difference in surface area. And so when we're telling people what we're predicting, we can say both. Forecast Builder generates both radial and flat thicknesses. Our official ice accumulation forecast is in a flat thickness. So when we generate those graphics, those images, and the prob messaging, we can tell people you can expect on flat elevated surfaces, like a picnic table, or like a, whatever else is flat and elevated. An airplane wing is what the measurement was designed for. You can expect about 1 inch of ice thickness on that. But on your power lines, on your branches, that ice is probably going to stick out about 0.4 of an inch, about 40% of what you would have otherwise. If you have any questions on this, let me know. Blame geometry, hashtag. Thank you, John. All right. Next thing you need to know, we need to talk about impacts. The impacts of ice should absolutely drive your message, period. The numbers are important. The impacts are more important, especially with ice. We just released, just for everyone, some new winter walk training, 3 lessons of freezing rain. The second one is almost entirely about impacts. Please check these out. Like, I'm not just trying to advertise it. I just want us all to be thinking about these things as we go. The impacts of ice should absolutely drive your message. Very little ice is needed to cause huge travel impacts. No friction, big problems. Freezing drizzle is probably the worst. And don't you just love it when you get a really light freezing rain and the roads are wet regardless, like it kind of looks wet, and then all of a sudden it's icy on a bridge. Huge problems for travel. Otherwise, ice thickness is only one consideration for other impacts. And we'll get into that a little bit more here in the next couple slides. And also the WSSI, we already saw that today. Those should be getting a little better, a little more input from wind and other items like that. Let's leverage those products and use them, because those are intended for impact assessment. Things you need to know in this topic. Wind is very important. Okay, wind is very important. Say it with me now. Wind is important when it comes to ice, because let's say you've got a 70-mile-per-hour wind on a clear day like today. At least it's clear out my window. You're going to break some branches. You're going to snap some power lines on 70-mile-an-hour wind. It's going to happen. Okay, now let's say you've got 0.2 of an inch of ice and a 40-mile-per-hour wind. Okay, we've got that extra weight. We've got that extra wind load. We are going to break some things. Okay, what if the wind is calm? If the wind is calm, it's probably going to take a 0.5 inch of flat ice in order to really start breaking things. That's right, a 0.5 inch. That's twice what our base criteria are for most of our ice storm warnings. So keep that in mind. Some of this, again, is going to be built into the WSSI in terms of incorporating multiple aspects here for assessing the potential to break things, basically, once we get into those higher end impact levels. Then, one last bullet here. We need to consider wind speeds long after the precip has ended. A lot of times that cold air stays in place, the ice remains up on the limbs, up on the wires, and then we get a secondary cold front. Oh no, secondary cold fronts come with wind, right? So we're going to put additional stress on those items even after the storm has passed. So again, think about impacts. Think about it at a base level. Okay, what could happen in this scenario? Shoot me a message or an email, or Chris too, or anybody else who's, stuck with talking to the world about ice. They'll have a lot to say, and it's good to be able to get a lot of inputs on this. More things you need to know. quarter inch of ice on its own will not produce ice storm impacts. But if you add any sort of wind, if you add any other factors, that's where we will start to break things. So we'll break branches, branches will fall on power lines, power will go out, people have to be dispatched. The more outages there are, the longer it takes to recover. And that's where we really started to get into some really high-end impacts. This is a just really quick and dirty chart, and it's not meant to be a strict guide. It's meant to be more of a display of how these things relate. You increase your ice accumulation, you increase your wind speed, and when you combine the two, that's how you tend to accelerate those impacts. Again, please check out the new freezing rain lessons in the walk. Consider wind load and other factors. We talk about it a lot in there. And we have to take that impact-based approach to ice storm warnings. Excuse me a sec. This is also an area that is just ripe for additional research. So again, please jump into this area if you've got that bit of ambition. All right, next topic, gathering and disseminating information related to ice. Again, it's not as difficult as it seems. Rule number one, ask for photos. Somebody says, oh, we got an inch of ice, or oh, my neighbor, I called and they said, we've got 3 inches of ice out there. Oh my gosh, let's get a picture. A picture with a ruler. Let's do it. You don't need a caliper, but if you have one, awesome, use it. But goodness, seek pictures. FRAM could provide a really good initial QC. Again, it's experimental. We want to see how it works, kind of see how things pan out. But even if you get a really good observation from some point, you might be able to correlate that in the FRAM to maybe a nearby area that might have received a little bit more icing, similar to what we do in a heavy rain or flash flood type of scenario. Also, actively seek observations. Freezing rain and icing is notoriously in sharp gradient areas, right? So we need to find a sharp gradient of observations so that we know what's going on out there. And by we, I mean the meteorologist working the event. You want to know what's going on. And then finally, when you send out these LSRs, just be clear. Gather all the information, provide it all clearly to the outside world. All right, so here's where it gets a little bit complex, and I'm trying to simplify it a little bit, but it can be complex but not difficult, right? So I'm talking about sending LSRs here. We do want to be very clear in the comments about what's being measured. So if we had 2-inch diameter thickness on a 1-inch branch, I mean, this stuff is weird, right? I built a spreadsheet and I've got it linked here. You're more than welcome to go in. You should be able to edit the pink cells. And let's just say that you measured, let's see here, the middle 2 boxes. I put 1.21 inches of total ice thickness. It's actually pretty similar to the photo A there. 1.21 inches of total ice thickness. I guess you had a caliper. But your branch is a 1/4 inch thick in there. Okay, what does that come out to? So you enter those 2 boxes, and then you look over in the green area, and we can say, oh, this is a flat ice equivalent of 1.2 inches. The radial thickness is 0.48. So really, you're just taking the total minus the branch or wire and dividing by 2. And the total diameter of the ice is 0.96. So you might put all that information into your LSR. Officially, you could say, because it's what we measure, because it's what we forecast, because it's what ASOS does, you might say 1.20 inches of ice. And then in the comments, you say measured 0.48 inches of radial ice thickness, which is a flat equivalent of 1.20. Again, I'm not trying to make it complicated. It's a lot of information that we're adding to this, but we're just being very clear and definitive. And so the more information you can add to it, the more questions it answers for anybody trying to observe. Again, blame geometry. I keep looking at John's comment over here. All right. Something you all need to know about is the CocoRa's freezing rain reporting pilot. Okay. They have started doing this in CocoRa's and have gotten quite a few observations where they've got people set up with dowels out there and across our great country. And then they give the opportunity to submit photos of those dowels. You can see a really good observation here, 1.16 inch thickness, which came out to 0.43 inches of total thickness once you removed the dowel out of there, and then pictures and comments on branches being broken. So that's all within the CocoRa's framework. I'm pretty sure that we can all access that. If you have trouble, please let me know or let the CocoRods folks know, and we'll make sure that Weather Service at least has access to that. This is something that I built because I like to build things. But this is outside of OAX here. We've had the joy of measuring ice on it like once since I built it. But you can see we've got a couple of flat surfaces to measure on. We've got a couple of PVC pipes or dowels to measure on. Basically, it's multiple ways to grab our caliper, head out there, measure, and then report it in the form of an LSR and or comments within our co-op. This whole thing to produce, I don't know, less than $100, and that's including the measurement device as well, which I think a set of calipers is like $18 for, at least for what we need it for. It's more than enough. Oh, this is one of my favorites. NWP ice prediction. This map is not an ice thickness forecast. I just want to say it one more time. This map and the numbers on it are not an ice thickness forecast. No, this is a single model prediction of the amount of QPF that's falling while the model is outputting freezing rain as the primary precip type. Okay, so this is not an ice thickness forecast. We see these routinely, right? Anytime that a model is spitting out ice, we're going to see these maps show up, and it's going to be people freaking out. And let's just, everybody remember, say it with me, not an ice thickness forecast. So we can go through, and first off, an individual model obviously isn't going to be correct, but also it's not going to account for runoff or drizzle or anything like that. So the FRAM does attempt to account for these things. There are a couple of websites that do run FRAM calculations. The HREF is my favorite. Sites like Pivotal Weather. If you are a paid subscriber, you can view FRAM data. Contrary to popular belief, I've never seen a cent of that subscriber money. But anyway, I'm not bitter at all. But yeah, so it's a charged feature if you want to see what the FRAM algorithm would turn this into. That said, even then, it's not going to be fully accurate. It's a one model read. I think we're all pretty aware of that, though. All right, one last topic here, and then I can let you all get on with the rest of your day. Talking about FRAM intricacies, okay? So as a whole, FRAM is statistically effective over a diverse observation. It tended to perform very well over the course of an ice storm. But it's not a perfect prediction. And if you only have 1 or 2 hours, or if you have a very specific scenario that you're going through, it may not work very well. And that's coming from one of the two guys who built it, right? So there are situations when your forecast and message should consider deviating away from FRAM. And I've linked a quick reference guide here that we sent out probably 2 or 3 years ago through Central Region, but it still applies today. I'm actually going to look at a bit of it here. Some of the common questions we get: why is the ice accumulation greater than QPF, and is that okay? Yes, it's okay, especially in windy situations. If you ever have a windy event, I want you to picture that you're driving your vehicle as fast as the wind is blowing. So let's say you're driving your vehicle 40 miles per hour. Will more raindrops contact your windshield than if you were parked? Yes, you're going to have more contacts on that elevated surface than if you were parked in place. So when it's windy, you tend to get more contacts on those elevated surfaces, like tree branches, like power lines. So you can indeed actually have a greater than 1-to-1 ice-liquid ratio. Feels weird, but it does happen. And so that's just something that I really wanted to put out here. Wind and also when you get into GFE and Forecast Builder, if you have very low hourly QPF, sometimes that defaults to go up above 1-to-1 ratio, and that's not necessarily correct. So I want you to keep this in mind. If you have sprinkles or very light rain where you actually have full rain drops falling, you're probably going to be over forecasting the rain amount or the freezing rain amount a little too much. Big drops mean more runoff. The problem is that most of our low end QPF freezing rain events are actually drizzle. And with drizzle, that can be a highly efficient freezing on elevated elements. There's almost no runoff of freezing drizzle because they're super cooled already, so they freeze on contact. All right, so I've got 4 scenarios here. Let's see here. One I already talked about. So very light freezing rain and wind greater than 12 knots. The FRAM is probably going to over forecast. And the big thing to note there is rain. Droplets, again, if it's a warm drop, you're going to have more runoff. If it's a drizzle and wind, you are not going to have runoff, and you're going to have a lot more contacts on those elevated surfaces. So as I jump over to the top right, freezing drizzle and windy conditions, you are almost definitely going to have a highly efficient icing condition. And a lot of times in those as well, your rain gauge catch is very poor because the drizzle is just very easily moving horizontal. So just keep in mind, freezing drizzle and strong wind, you want to aim very high in your icing amounts. If you have very light freezing rain and light wind, then you need to aim probably lower than what the FRAM is spitting out. Again, it's probably going to be very light QPF anyway, so it won't matter too much. Something to keep in mind. Seems that with freezing drizzle and light wind, FRAM does a pretty good job. May forecast slightly for very low end freezing drizzle, but something to keep in mind there. And then the other one I wanted to point out is if you've got a full on freezing rain event and you've got a wet bulb right around 31 to 32 degrees, so near freezing, and a light wind, you're probably going to have more runoff. And so FRAM is probably going to over forecast in that near freezing light wind event. And that's just the way that it's set up in the current peer-reviewed method. Typically in this situation, you can expect an ice liquid ratio between 0.2 to 1 and 0.7 to 1. And I know that's a pretty wide range, but you'll notice that it's the low end of the range. So that's because in a true freezing rain event, you've got warm drops. And if you don't have a lot of wind to remove that heat release, then you're probably going to have quite a bit of runoff in that scenario. So things just to take away, and then I'll let you be on your way. Key takeaways and wrap up. First, impacts. Please think about the impacts. Please, if you've got a scenario, reach out and ask us what the impacts have been in similar scenarios in the past. We'll gladly chime in and help. Leverage the WSSI, leverage your other resources, leverage your partners out there and say, hey, if the ice is this thick, what do you expect will happen? Just straight up ask them. That's probably your best resource. Flat and radial, it's not that complex. Blame geometry. Yeah, it's strangely easy and also annoying, and I get it. But please just provide all that information and provide it very clearly internally and externally so that people can understand it as they need to. Consistent ice measurements, somewhat complex, but not difficult. Feel free to find that link and use that ice calculator in the spreadsheet. Again, reach out if you have any questions. Happy to help and try and simplify it a little bit. FRAM is not perfect, but it's pretty good. And it can be situationally improved. So keep in mind some of those scenarios that I laid out. Even another scenario would be if you have a really, really warm layer aloft and a deep one, you're probably going to tend towards the lower end. You're going to have more runoff. So, we have to think about these things physically, which thankfully as meteorologists, we've all got plenty of experience in that, but don't hesitate to think about it. And again, speak to the impacts. Reach out with any event-specific questions. You all have my email. There are 3 Barjenbruchs. I'll be the Brian. So reach out anytime. Hopefully that satisfies a need and maybe clarifies a few things without adding too much more complexity. But if anyone has any specific questions, I am happy to give it a shot.